Okay, so welcome to the EPR meeting. So just some rules first. So this talk will be recorded and it started actually now. So if you really don't want to be on this video, yeah, just don't appear basically. It's in your control. Then just please mute yourself during the talk because sometimes it's actually, you don't recognize if there's some background noise in your flat or something, and it can be quite distracting. But you can raise your hand also during the talk if you want. Not sure if Lizzie will take questions, but we will see. Sometimes it's okay. And there, usually you can click on like participants, and then you can raise your hand, and then I should see it that somebody raised his hand, and yeah, I can interrupt. Okay, so with this today, we have Lizzie Canarie giving a talk, and maybe actually her cat will appear, and cat's name is Buffy. So Lizzie studied at Arizona State University, and now she's doing her PhD with Stefan Stoll at the University of Washington in Seattle. And her talk will be about predicting decoherence of prototypical spin qubits in frozen solutions. And Lizzie, you should be able to share your screen yourself.
Yes, screen share. Oh, continue. Continue. All right, is that, you're seeing that? And there we go.
Perfect.
All right, so, one second, sorry, let me just adjust. So you all are, my camera's this way, my second screen is this way, so if I'm looking that way, I'm looking at the screen, but all right, thank you all for joining in. Thank you, Nino, for organizing this and inviting me to talk today. Today I'm going to be talking about predicting decoherence of prototypical molecular spin qubits in frozen solutions. But since this is an APR meeting, let's be real and let's call them molecular spin centers instead of qubits. So just as an overview for what I'm going to be talking about today, first I'm going to talk about coherence and decoherence. They're terms we're familiar with, but we don't necessarily think about the intricacies of them on a daily basis. Then I'll talk specifically about nuclear spin-driven electron decoherence. And then I'll move on to experiments and predictions that we've done, and I've done in collaboration with Sam John in my lab, and then talk about future outlooks for this project. So what is coherence? Coherence is when electron spins are coherent, you can manipulate them and refocus them to get back information. And so here's just a cartoon of what it looks like when spins are coherent. They're processing at the same rate, so we can refocus them to gain information out of it. Now, here we have spins aligned in an external magnetic field. They're pointing in the same direction, but there are other processes contributing, which, I don't know if this chat, there are other processes contributing. So the spins are now no longer in phase, and they're not coherent, we can't refocus them, we can't get information out. Now, things being coherent, or spins being coherent, is really important in pulse CPR experiments, so we can get the information back, so that we can perform our experiments. And longer coherence times means we can investigate further distances, it means we can perform more intricate experiments. It's also important in quantum information sciences application because the longer coherent times, the longer that they can speak and qubits can perform operations. So how do we measure decoherence? I think most of us are probably very familiar with the Hahn-Echo sequence that we have here. So we have our pi/2 pulse, wait some time tau, apply a pi pulse, and wait some time tau until we record our echo. And we get one spot on our echo decay curve. And then what we do is we vary our tau time and we increase it, and then we get a decaying intensity of our echo, and we record that, and that is what our decoherence is. Now, quantum information sciences or APR applications are really limited by our coherence times. Now, what causes decoherence? There are a few common sources. First is longitudinal relaxation or spin orbit coupling or tunneling. We have instantaneous diffusion, nuclear-driven electron spin decoherence, methyl group rotation, vibrational motion, molecular tumbling, and the presence of dioxygen or other paramagnets in the system. But for the purposes of this talk, and for practical purposes, since we can isolate out a lot of these other types of relaxation mechanisms by concentration or temperature, what we focused on is nuclear-driven electron spin decoherence. So here we have an electron in purple, and surrounding it in teal are nuclei, and all of the nuclei contribute to decoherence on the electron spin. So we want to make a predictive model for being able to know what our phase memory time, or our TM, will be for an electron spin in a frozen solution. So we might be familiar with the stochastic model of nuclear spin diffusion, where we have an electron that is coupled to two nuclei with hyperfine coupling, and they flip-flop with a flip-flop rate W. And that flip-flop term actually introduces a time dependency to the frequency of the electron precession, as well as the hyperfine coupling experienced by the electron to the nucleus. But what drives the flip-flop rate? There is no deterministic model for that. So is there a deterministic picture we can paint for nuclear-driven spin diffusion, electron spin diffusion, or decoherence? So here we have our electron, and it's in an external magnetic field, B0. And then we have our hyperfine coupling because there's a nucleus nearby. And the external magnetic field is pointed in this direction. And then we have this offset, the nuclear coupling hyperfine. And then we have the hyperfine coupling to the electron. And that creates this effective magnetic field experienced by the nucleus. Now, when there's a transition from alpha to beta of the electron, this could be the superposition of states, or it could be upon an application of a pi pulse. The electron spin flips, and now the hyperfine coupling has changed sign, so the effective field that the nucleus experiences is at a tilt from the direction of the magnetic moment of the nucleus. So what happens? The nucleus precesses around that effective magnetic field and introduces time dependency in the hyperfine coupling. So this is kind of not necessarily exactly what's happening, because we can't exactly know what's going on with spins, but this is kind of the picture of where we're at in our understanding of a deterministic explanation rather than the flip-flop rate that is stochastic. So if we want to simulate this, right, how do we do that? There's a huge scaling issue for simulating nuclear spin or electron decoherence from nuclear spins. And the first is that to describe n spins, you need 2 to the n basis states. So to give you an idea, if we had a spin system with 265 spins, that would require as many basis states as there are numbers of atoms in the universe. So that's basically impossible to calculate without a quantum computer already. So can we approximate a signal? And if we can, how can we break the signal down into something that's possible on existing technology? All right, so here I have just a tempo molecule with the electron denoted in purple, an external magnetic field. Now it's surrounded by water. And so what's going on in this system, we have the intramolecular couplings of the protons on the water. We have the intermolecular couplings of the protons on different water molecules. And then all of those protons are also coupling to the electron. Now the electron can't differentiate these types of processes, so it's all the same. It experiences them all the same, just in different intensities. And you can see this is a mess. This gets really complicated way too quickly, and you can see why you can't calculate anything this way. So let's go back. How can we do this in a better, more simplified way? So first, we can limit it to spins within a certain distance of the electron. So let's only include protons within a radius r of the electron. And then what we can do is look at clusters of protons that are coupled by a certain coupling strength, so kind of a neighbor cutoff and how strong their coupling is. And let's create a cluster based on those coupling size. So we have cluster size 1, cluster size 2, 3, 4, etc. And so what we do is calculate the signal from each cluster based on the clusters are based on that coupling cutoff, then multiplicatively combine each cluster signal and do an orientation average, and then converge with respect to the necessary radius, the necessary neighbor cutoff, and the necessary number of orientations. And this is based from Yang and Liu's work on the couple or cluster correlation expansion method. So for our predictive method test, we use these organic radicals. We have tempo, D18 tempo, and a trityl radical, P1 TAM, that was generously gifted to us by Valerie Kramstoff and Benoit Dreschard. So tempo and D18 tempo are all the same except the per day duration of the protons in D18 tempo. And they both have the nearby methyl groups. And P1 TAM has those methyl groups pushed out pretty far. So those are kind of just two different types of radical environments. So just looking at this experimental, these experiments were performed in 1-to-1 weight-to-weight glycerol to water. H2O and regular glycerol, not D2O. And so here we can see the experimental curve for the P1 TAM at 20 Kelvin. And we can look at the first principle structure-only based method where in red, and that's the simulation we get. So we have a pretty spot-on quantitative prediction for this experimental echo decay. And Sam did a great job with these simulations. So you can see the overall behavior is well predicted, the time scale is well predicted. For D18 tempo, we now have the kind of intense ECM that we didn't see in P1 TAM, but we're even able to model that ECM, and there's only a slight discrepancy in the overall time scale, which that discrepancy can be attributed to molecular dynamics errors. So it's pretty, but again, a very good quantitative prediction of the decoherence behavior of D18 tempo. And then finally, we can look at tempo at 20 Kelvin, and we see this kind of early deviance from this kind of stretched exponential shape. They're not clearly resolved ECM effects. It could be some ECM, it could also be some methyl tunneling, but we can see there's some reproduction of that kind of secondary shape from the inclusion of ECM in the simulation. And again, the overall time scale is really well matched. So what we can conclude is that we're able to quantitatively predict decoherence behavior and time scale from just a structural based method that is based on first principles. So, but is there anything else we can learn, right? Like this is cool and very useful by itself, but we have all this information, there's a wealth of knowledge, what else can we figure out? And what would be a useful question to answer? And one useful question, if you are designing either a molecular spin qubit, or if you're looking at a site on a protein you want to label, you want to figure out how long your phase memory time is and kind of figure out what protons could be contributing more. So what about the local environment contributes most to the decoherence? So here, we kind of came up with this idea, what if we looked at, so here's the overall full system decoherence trace. So this is N nuclei. What if, and then here we have the 1/e point, so that's the TM. If we're familiar with the TM stretched exponential equation, 1/e of the original intensity is where we have our TM. Now, let's look at this system where we take out one nucleus. We take out nucleus I and we have N-1 nuclei. So let's say the full system had 1,000 nuclei. If we look at the system with 999 nuclei, we get this curve. And we see that there's a change and an increase in the phase memory time. You can see that right here. And we're calling this the delta TM. So this is the delta TMI. So for removing the ith nucleus, we have this much increase in phase memory time. Now, I want to point out, this is grossly exaggerated on what a delta TM looks like, but if I made them on the scale of nanoseconds, you wouldn't be able to see them. So this can tell us, okay, which protons individually are most responsible for decoherence. So here, Sam did a great job with these plots. So here we have tempo. This purple sphere is just the electron, and surrounding it are water molecules. And so the darker blue sphere, the more that that proton contributes to decoherence behavior. So you can see far out, pretty much all of the protons are white, so they're not contributing much. But as you go in, you get this kind of hot ring of fire where there's a lot of decoherence due to these protons at kind of this intermediate range. And then when you get closer in again, you see there's less contribution from the very close by nuclei. And so this ring of fire actually kind of demonstrates that spin diffusion barrier, that nuclei close to the electron don't contribute as much to decoherence. And you can see this on a plot of distance from the electron, so that how far away the nucleus or the proton was from the electron, and the change in TM. So if you remove that single electron, how much do you increase your TM by? So you can see kind of in this shorter range, there's not much of a change of TM. It's less than 10 nanoseconds. But as we get kind of about 5 to 8-ish angstroms, we get this big effect on TM, where the most highly contributing to relaxation or decoherence are almost 30 nanoseconds change. So if we were to remove those protons, we would increase our phase memory time by 30 nanoseconds, which guides kind of our ability to tune a system, especially for people who are interested in structurally based, or like, saving time at the bench. So what proton should I remove from my system before I go and synthesize it? And we can actually see the spin diffusion barrier for all of the samples. So D18 tempo, it's not as kind of rigid as the other ones. We see kind of some intensity below that 4 angstrom cutoff. That's likely due to the large ECM effects that we're seeing in the D18 sample. But it does kind of follow the trend again. And then for P1 TAM, there aren't actually any protons closer than 4 angstroms. So we just see kind of the large drop off in decay as you move further out. So this is all really exciting that we can kind of visualize the spin diffusion barrier, that we can point out which protons are contributing most to spin decoherence, and that we can tune systems based on this approach. So just as a conclusion, we have a structurally based full quantum model that just requires input structure and solvation and outputs decoherence times. It's a quantitative prediction that matches experimental data. And it's an application, a possible application would be materials design for quantum information sciences, or the dream would be for site-directed spin labeling, that a more accurate prediction of phase memory time, so you can really decide if your site of interest is good for spin labeling, has a long enough phase memory time to do the experiments you're interested in. So with that, I'd like to acknowledge the Stoll Patrol, particularly Sam John for his awesome simulations work, and Valerie Kremstoff and Benoit Dreschart from the University of West Virginia. I would also like to thank the National Institutes of Health for funding me for the last 2 years. And thank Nino for organizing this. I'm open for any questions.
Okay, Dani?
Hey, Lizzie, thank you very much. Very nice and interesting talk. Now, in the end, you showed the protein with different spin labeling sites. And above, you showed the different water clusters around the tempo. Now, you could imagine easily that the cluster size distribution you find in the bulk water might be different from what you find typically in protein side chains. Could you comment on this?
Yeah, absolutely. So this is the application of protein spin labeling kind of prediction. That's down the road. We're not there yet. Originally, we got on this project. That was kind of the goal, but we realized proteins are a lot more complicated, right? There's a lot more to model with the side chains, with the water packing around the protein, exactly. So the model is not there yet, but it would be, so the way that this works is like you do a geometry optimization of your structure. So you'd have to use, a crystal structure and then geometry kind of hold your protein rigid, attach your spin label and optimize the rotamers, and then do solvation in MD, and then get out the quantum model. So yeah, would consider that.
Sure, of course. That's very complicated, yeah. I know, but
yes.
I actually wanted to ask something more, something simpler. So the clusters in your water solution, which kind of clusters are contributing how much? Can you say something like this, or is there no such trend for different cluster sizes? Because the cluster sizes will be different on the protein. Oh yeah, so the clusters, no, so it's it ends up being the overall cluster size are contributed. So you have to figure out, so like for tempo, these molecules, we were able to get away with cluster size 2, but I would expect probably on a protein, you would need larger cluster sizes. Mm-hmm. That wouldn't surprise me. So, but that is something you would have to optimize system to system. Okay.
Gunnar?
I also like the talk very much, very interesting results. So I have a rather technical question. You see this decay of the contribution towards long distances, and my naive prediction would be it's an R to the -6 behavior. Did you try to fit this somehow?
That's actually on my to-do list for this weekend. Yeah, because it's like R to the 6 or R cubed, something like that, yeah.
Okay, then Maxime?
I have question actually to this slide as well. Have you tried to plot this delta Tm not for individual spins, but like making a histogram for all spins at a certain distance? Because certainly when you increase the distance, individual spins do less, but there are more of them.
We have plotted it that way, but we thought that this, especially in kind of the hot zone, that it wasn't as informative in the hot zone. But yeah, we have plotted it that way too. I don't have those plots readily available though.
Okay, then Asif?
Thank you, Lizzie, for a wonderful talk. In slide 12, you show the simulation and experimental overlap.
Mm-hmm.
I was very amazed, like in simulation, how do you account for the other factors of decoherence? So I think you just considered hyperfine coupling. What about the other factors?
Well, so we chose concentrations that were low enough to prevent instantaneous diffusion effects.
Mm-hmm.
We're working at 20 Kelvin, so motional effects are pretty limited. So we actually, it turns out that the primary contributor at, below 70 Kelvin to T2 limited samples, or samples where their TM is limited by T2, it's just nuclear spin diffusion is the primary contributor. So that's mostly what's going on. And we would say maybe there's some methyl tunneling for the tempo maybe that's happening that we are not accounting for, but we're just accounting for ECM, nuclear quadrupole interactions, and that's about it. And
so
hyperfine.
Suppose like I've seen like some papers where people use d orbital complexes like vanadium complexes for qubit purpose. So will your model fit there, because then you will have spin orbital coupling? And so I think there is already a paper by Dana Friedman for different vanadium complex, and she also has something similar result. Did you try to fit those kind of decoherence curve?
We looked at that, but we decided for this first paper, which we've submitted to JPCL, we're just doing the organic radicals. The metals, there's a little bit more going on with the d orbitals. So yeah, this is the starting point, but that's an interesting question, something we considered looking at.
Thank you.
Okay, then Fraser McMillan.
Hi, Lizzie. I didn't see a great difference between the D18 and the tempo in that distribution function. What about if you change the solvent and deuterated the solvent? Does it make a big difference?
Yeah, so it does. If you do it in D18 or D8 glycerol and D2O, the phase memory times are different. Obviously they get much longer, and for tempo and D18 tempo, they're different. The reason I'm not showing that data is modeling the nuclear quadrupole interactions from the D2O gets very complicated, and there's an oscillatory behavior that ends up not working well with this cluster correlation expansion method. So those time scales are not well reproduced. So we tried really hard.
Can you just show us the slide where you have the distributions for your hot? This one. So okay, the y-axes do have different magnitudes. I wanted to compare the tempo and the D18 tempo.
Yeah, so tempo and
they're about the same in the delta TMs.
Mm-hmm. The difference is really kind of this early intensity here that we see in D18.
Okay, thank you.
Thanks, Richard.
Okay, Angeliki?
You're muted.
Angelika, you have to unmute yourself if you want to talk.
Yeah, sorry. Good point. Very nice talk. Thank you. I have a question. Like the measurements were done at 20K, and I was wondering why this is. Like, did you see any difference at 50K? Because this is where normal nitroxides are measured, and even higher.
So I did the experiments from 20 to 60 Kelvin for all the samples, and I didn't see any real temperature dependence in the decay behavior below 60 Kelvin. I just showed the 20 Kelvin because that's the one that is like for sure the most frozen, like it's, you know, it's the coldest, so it's the least likely that we can really argue that we have eliminated it to just nuclear, or primarily nuclear spin diffusion.
It's surprising that the decay is the same between this range of temperatures, no?
Not really. So there's a Eaton paper that shows that below 70 Kelvin, that this is consistent with below 70 Kelvin, as long as other relaxation effects like instantaneous diffusion aren't a problem, you don't expect changes in nuclear spin diffusion.
Thank you.
Okay, then Eric.
Hi, Lizzie, that was terrific. I had a question which was related to Fraser's. I was wondering about partially deuterating your water. Because presumably because I think you were, what were you doing, lengthening TM by 30 nanoseconds per nucleus?
So yeah, these are not additive.
Statistically by experiment, if you see what I mean, by loading different amounts of D2O in.
Yeah, and that's actually Sam is working on those simulations right now. That's kind of, we want to measure that, but you know, can't go in. So we're working on that.
Thank you.
Okay, then I have maybe a selfish question. Could you simulate this during a spin lock? So looking at the decay of your magnetization while irradiating, or would that kind of screw up some of the details in the?
So irradiating to like do polarization, or?
Just really spin locking. So do a pi half pulse and then just do a irradiation along basically the magnetization of the electrons. And
I honestly don't know, but because you're introducing a different, you know, process, it would no longer just be nuclear spin driven decoherence, right?
Well, so the idea, the quick idea I would have is that you would kind of semi-decouple actually part of the hyperfine interaction, but there shouldn't be an additional decoherence pathway. I mean, it's just another dynamics that might partially average some stuff, but it's not. So
yeah, I mean, I think it's probably possible,
okay.
But I don't think as is it is possible. I don't know honestly.
Okay.
I don't think Sam is on this talk. He would be able to answer better.
Okay. Then I don't see any other question. Thomas?
Hey, just like to what Nino said, I think that would be actually pretty good because that would be a simple R1 row experiment, like they did in Colombia, right? So then you would just spin lock it and you work on you get rid of the hyperfine interaction. You just extract the R1 with the R2 row pretty much. Is that what you're talking about?
Yes, or T1 row or T2 row. It's just in a rotating frame relaxation time. Because I mean, if the calculations you're doing are deterministic, I think this should actually work. It just depends whether this clustering actually still works. I don't know because I don't know the details. Okay.
I haven't done any spin locking either, so I don't know.
And then Lizzie, there was a paper I was looking at, like a 1980 something paper, and they I mean, they didn't really look in detail as you guys did, but they looked at the T2 effects as it's like done with nuclear interaction. Was by an Italian guy, and I forgot his name. Sorry about all the Italians. And a New Yorker guy, and they looked how the T2 is affected in distance. I remember it was R to the 6 dependence. So just to let you know, since that came up.
Yeah.
Which makes sense.
I'm not familiar with that paper.
Yeah, I don't know the name either.
Okay. Any other questions? Now's the time. If that is not the case, then I would thank Lizzie again. Applause might sometimes be not very.
Thank you.
Stop the recording.